Welcome back. In this lecture, we will talk about depth-first search. So, with this idea of having a set of frontier nodes, depth-first search is going to treat this as a stack. So, in other words, it's always going to select the last element that was added to the frontier. And so, in doing so, it's going to go down deep. It's going to keep building on the current path. It's not going to stop and revisit it later. And so, as we do that, we will be diving down deep into the structure of the state space looking for a solution. Hence the name depth-first search. So let's look at this example. So if the start node is at the top, this diagram is kind of nice because it's showing the order in which the nodes are visited. So we're here at this initial node or state, and the first node that gets expanded, let's just work left to right, is this one labeled 2. Now, there's this node in orange. That node does not yet get explored because we are not going to go and expand another child node of node 1. Depth-first search is going to add in the most recent node to the frontier. So even though we haven't checked out all the neighbors of 1, we're going to instead investigate more of 2. So hence we go to 3, 4, 5, and 6. Now 6 has no further neighbors. So, and it's also not a goal state. So we have to now check out another path. Well, this path was no good. 6 is not worth looking into because it's not going to lead us anywhere. So we can forget about that. Okay, so now we check 5. Well, 5 had one child node, meaning 6. Does it have any others? Well, the answer is no. So we now know that 5 can't get us anywhere either. So that guy goes away. So now we have node 4. Well, there was an unexplored neighbor of 4, and that's 7. Okay, so now what do we do? Well, by depth-first search, we check out 8 and 9. But again, 9 is another dead end. So forget about it, and now we're back at 7. Well, 7 has another neighbor, 10, and 10 has a neighbor, 11, but that's also a dead end. So forget that and forget that. 7 has no more neighbors to look at, and we know everything that we checked didn't get us anywhere. So 7 is not something we want to keep anymore. Now we have 4. Well, we checked all the neighbors of 4, and they didn't get us anywhere, so we can get rid of 4. Now we're back up to 3. And so 3 has one other neighbor we haven't looked at. It's 12. But you know what? That doesn't get us to a goal either, so forget about it. So this means that 3 is something we can also forget about. So now we're back at 2. So 2 still has another neighbor, 13. And 13 has a neighbor of 14. And 14 has a neighbor of 15. 15 is not a goal, no more neighbors, so that's not useful. So now we check the other neighbor of 14, which is node 16. And then we look at the children of 16, and the first one is this orange node, which, you know, in this example is a goal. So we've reached the goal node. We have not needed to expand everything. And notice these things that we erase, we don't need to keep track of those. So what's nice about depth-first search is what we need to maintain in memory is only linear in the depth, because we only really need to keep track of one path at a time, and you know the other things we are either not explored or we've explored and we know they're no good. But as you can see here, if we have an optimality criteria, all the way up here is this guy here, this other neighbor of node 1. And we've been spending all this time searching these other things, and that guy was right there. And if you have a cost that's based on the number of hops, that one circled in blue is much lower cost than the goal we wound up at. So it could have issues with optimality as well. Also, let's say that the goal node was way over here somewhere. Again, we don't know where the goal node is. We could wind up expanding out the entire state space, which would be an exponential runtime in the worst case. The other thing is we haven't even considered the case where there is cycles in the graph, where you're going to go back and revisit some states. So you could have a case where you're searching down and you're going, from state 1 to 2 to 1 and over again. And this could just go on forever. Now, later on, there's some ways to counter these, but for depth first search by itself, these are some of the key problems. So here's a quick exercise. You could see that, which shaded goal will depth first search find first? Well, if you're going to assume it's doing expansion left to right, it's going to find D. If you're going to assume the expansion the other way, then it'll be on A. So we've already covered some of these questions. So is it guaranteed to find the path with the fewest arcs? And the answer is no. And what happens if there's, if you have an infinite graph where there's cycles, it's just not going to terminate. It's going to run forever. And time complexity as a function of the length of the path selected, this is going to end up being exponential. And the space complexity, that is going to be linear. And so how does the goal affect the search? Well, it causes it to stop. But the placement of the goal, deeper goals are going to lead to longer searches. Goals that are, in a different part of the search space that you're not expanding right away is also going to lead to longer runtime as well. All right, so this concludes the section on depth first search. Stay tuned for more content.